in this video, we will see the voltage and current relationship of DC, shunt and series generators. So first we will start with shunt generator. So let me draw the diagram or circuit diagram for a shunt generator so that we can solve the expressions with the help of the diagram. So in shunt generator, the field winding number of turns will be high and it is connected in parallel with the armature winding. And this is the generator, this brush, which is connected to a load. Generator is connected to a load, and this is load, and this is generator. The induced EMF is E here, E or EG, right? So this is A, armature winding A, this is AA, and these are the brushes. There are two brushes, right? Now the current or the voltage, first let's start with the voltage. The voltage across this load, the voltage across this load is represented by VT, which is terminal voltage. VT means terminal voltage. If it is V, then it is input voltage. If it is VT, it is terminal voltage. Now the generator generates a voltage E or EG, and the current in the armature connectors through the induced EMF will be IA. This will be flowing through the armature connectors, and this IA is again divided into two. One is IL, load current. IL is flowing through the load, IL, and IA, the remaining portion of IA is flowing to the field winding, that is represented by IA sketch, because normally we will denote the field winding current as or the current flowing through field winding is IF, but the field winding here is connected in parallel with the armature winding. So we are representing the field current flowing through this field winding as IS sketch. So IS sketch is the current flowing through this winding, right? So this is A1, A2 or AA, and this is F or F1, F2, right? So these are the current and voltages of the DC shunt generator. Now from this, the voltage and current expressions or current relations can be derived by, now see here, this IA is equal to IS sketch and IL, right? This IA is divided into IS sketch and IL, right? One is going to the load, the other is going to the field winding. Now simply IA can be written as IA is equal to IL plus IS sketch, I suffix L and I suffix S sketch. This is the value of IA, right? Next, from this, now voltage across the load VT. Now voltage across the load VT can be expressed with the help of IS sketch. So IS sketch is equal to VT divided by RS sketch, because the voltage across this load and the voltage across this field winding both seems to be parallel. So the voltage drop will be also equal in load and in this shunt field winding. So IS sketch, the shunt current is equal to voltage across the terminal, voltage across the load or the terminal voltage divided by the shunt field resistance, right? So this is the value of IS sketch. This is the value of IS sketch. Now the value for voltage, I mean induced EMF, can be expressed as E is equal to Vt plus, right? The generated EMF is generated in armature winding, and this this induced EMF supplies the energy to the load. So Vt plus the armature itself will have some drop, right, which is represented as Ia into Ra, plus here we have two brushes, so the brush will have some drop, so plus V brush, right. So the induced EMF E or Eg of shunt generator is equal to the induced EMF supplies its energy for the brush drop and armature conductor drop and the voltage across the load, and supplies the voltage to the load, right. So Vt plus Ia Ra plus V brush. This can be also expressed as Va. So Va means voltage drop across the armature winding or armature conductor is equal to Ia into Va is equal to Ia into Ra. So due to voltage drop, we are expressing it as Ia into Ra. So where E is equal to 5P N Z divided by 60A. This is the expression we have derived for induced EMF of DC generator, right? E or Eg, right? So this is expression for this, and this is equal to this whole term, right? So E is equal to Vt plus Ia Re V brush, where V brush will be very negligible. If in question they have mentioned to include V brush, then we need to include the voltage drop in solving the question or answer. If they not mentioned the V brush, then we can neglect the V brush, right? So you will have a doubt that why we have not considered the voltage drop across this field winding. That is VSH is equal to ISH into RSH. We have not considered this in this induced EMF expression, voltage drop expression, because the resistance value of this field winding is high, right? So the drop will be very less. So we have not considered this. So in other words, the maximum current will be flowing through the load, not towards the field winding, right? So we have not considered this ISH or RSH drop here, right? So this is the current expressions and this is the voltage expression for DC shunt generator. Now we'll move on to DC series generator with the diagram. So the circuit diagram for DC series generator is here the armature winding and the field winding. Here the armature winding and the field winding both will be connected in series, and the number of turns of the field winding in series generator will be very less compared to the shunt generator, because the resistance of this field winding in series connection will be very less, as number of turns is less. This is load connected to the armature, this is G, this is A. These are the brush, the shaded portion of the brush, and this is S1, this is S2. Next, the voltage across the load, the voltage across the load is Vt, terminal voltage, right? Plus minus. Here also in this case also is plus minus, right? So now let us assume the voltage and current direction. Now this generator will generate a voltage, induced EMF, through which we will get a current Ia, armature current Ia, flowing through the armature conductors. The Ia will flow through the series field winding. So the current flowing through this will be ISE, right, or IF, right? So IF. and the same current when flows through the load will become as IL, right? Will be denoted as IL when flowing through the load. So and the EMF generated here will be EREG, induced EMF, or generated EMF is EREG, right? So this is going to supply, this EREG is the generated voltage or induced voltage EMF. This supplies the internal drop, and it supplies the energy to the connected load, right? Now for this circuit or for this series connection, the current expression and voltage expression can be expressed as, now let's start with IA. Here IA is equal to ISC, which is equal to IL. As I told here, armature current flowing here will be flowing through this series field winding. The same current will be flowing through the load IL, right? So IA and ISC and IL, three currents are equal in this series connection. Now let's see the induced EMF or generated induced EMF expression or voltage drop expression for series connection. So E is equal to Vt plus, so generated voltage E supplies the energy to the load, so it is represented by Vt. So Vt plus, it also supplies the armature conductor armature winding drop, which is IA into RA plus the same current is flowing through this series field winding. So the resistance of this is very less, so we need to include the voltage drop because it is in series connection. So IA into the resistance of the field winding is RSC plus there are two brushes. The brushes will have negligible voltage drop, so we need to include the brush drop for the expression purpose, so V brush. So the induced EMF E is equal to the energy supplied to the load Vt plus IRA drop. IRA drop means the voltage drop across the armature conductors plus IRC drop. IRC drop means voltage drop across the series field winding plus internal brush drop, right? Normally brush drop will be very less and negligible. We no need to include V brush based on the circumstances, right? So E is equal to Vt plus, here IA both are common in this product term, this product term, so IA is taken outside as common, so RA remaining RA plus RC plus V brush. This is the induced EMF expression or voltage expression for series generator, where EG is equal to, or E is equal to where E is equal to 5P NZ divided by 60A, which we have derived in induced EMF of DC generator, right? So this is the current expression for DC series generator current relation, and this is the voltage relation or voltage drop relation for DC series generator, right? Similarly, we have the voltage and current relation for DC compound generator. We will see that in next video. Thank you.